Electrostatics in 5 minutes or less. The big equation that governs forces for electrostatics is similar to the one that governs forces between two objects with mass. Q1 times Q2 times K divided by R squared. K is a constant, 9E9. So, if I have a 6 microcoulomb charge and a 3 microcoulomb charge, and I want to know the force between them, it will be 9E9 times 6E negative 6, because micro means negative 6, times 3E negative 6. Let's say they have a distance of quarter meter apart, 0.25. Make sure you square the 0.25. I'm not going to solve it, it's going to take too much time. Now, the next thing is field. Field is a lot like force, except what we're going to do is we're going to move one of the charges. So it's KQ over R squared. If you have a positive charge of 6 microcoulombs, and you wish to know what is the force, what is the field, 0.3 meters away, K, 9E9 times 6E negative 6, because again, micro is negative 6, divided by 0.3. Again, make sure you square the 0.3. Oftentimes, though, what is going to happen is you're going to be given, at this point, there's an electric field of, say, 5,000 newtons per coulomb. And it wants to know that if on this point you put a 6 microcoulomb charge on that point, what is the force to it? The force is the field times the charge, which in this case would be 5,000 times 6E negative 6. Again, the negative 6 because it is micro. Keep that in mind. A lot of the wrong answers are chosen doing 5,000 times 6 as opposed to 5,000 times 6E negative 6. Next thing, charges in general. If you have two positive charges, they will repel each other. If you have two negative charges, they will also repel each other. If you have a positive charge and a negative charge, they will be attracted to one another. Keep in mind, it doesn't matter if one of them is very strong, say 8, and the other one is very weak, say 2. The force will be equal because of Newton's third law, equal and opposite reaction. Next thing to deal with is fields. Field is the direction that a positive charge will accelerate away from it. It's not the way that it'll move, it is not the way that it is moving, it's the way that it'll accelerate. And again, we're talking about a positive charge. So, for example, if you have an electric field that's going to the right, and you place a positive charge into the middle of it, it will accelerate to the right. If instead you put a negative charge in the middle of it, it will accelerate to the left, because negative charges will do the opposite thing that positive charges will do. Next thing to talk about regarding fields is what do they look like around a positive charge. If I put a positive test charge right here to the left of this positive charge, it's going to want to go away from it. It will accelerate away, so the field would be pointing out to the left. Likewise, the field around a positive charge looks like so. Negative charge looks similar, except that the arrows are pointing towards the charge instead of away from it, because a positive test charge placed somewhere in here would actually want to accelerate towards the negative charge. If you have two charges, a positive and a negative, it will create a field like so, because all positive charges would want to get away from this positive charge on the left, while at the same time being attracted to this negative charge on the right. If they were the same charge, say two positives, your field will look like so. Again, the arrows for this are going to be pointing away, because positive charges would not want to go near either one of these two positive charges. If they were negative, the field would look exactly the same, except that the arrows would be pointing in the opposite direction. Capacitors depend upon three things. They depend upon the material in between them, they depend upon the area of the plates, and they depend upon how far the plates are separated. They do not depend on charge. That's a trick. You will see it. They do not depend on charge. They do not depend on voltage. Again, it's a trick. Don't fall into that. Last thing is that the energy is Q times V. So if you have a lightning bolt that discharges 50 million volts for 35 coulombs of charge, 50 million times 35 will tell you the energy that was discharged.